Section 12.5, the normal curve. Upon completion of this section, you'll be able to understand properties of a normal distribution, understand and apply the empirical rule, calculate a z-score. So we're going to look at the distribution of some different types of populations. So a rectangular distribution occurs when all the observed values occur with the same frequency. J-shaped distribution, the frequency is either constantly increasing, as we see on the left, or constantly decreasing, as we see on the right. Bimodal, two non-adjacent values occur more frequently than any other values in a set of data. Skewed has a tail on one side that's longer than the tail on the other side. The histogram that we see on the left side is skewed to the right, and the histogram that we see on the right side is skewed to the left. Skewed distributions, we can smooth these to form curves. And what happens is the skew pulls the mean towards the skew. So if you notice the one on the left side, the mode is the peak, the highest. The median's a little bit above that, and then the mean is being pulled toward the skew. Likewise, with the skew to the left, the mean's being pulled to the lower end. The normal distribution is the most important distribution that we study in statistics. The properties of a normal distribution. The graph of a normal distribution is called a normal curve. The normal curve is bell-shaped and symmetric about the mean. The mean, the median, and the mode of a normal distribution all have the same value, and they occur at the center of the distribution. If we roll a die 10,000 times, we would expect the histogram of the frequencies of the outcomes to have what shape? So if we think about this, there's 6 outcomes, 1 through 6, and we would expect that they would all occur with the same frequency, so we would expect this would have a rectangular distribution. The distribution of the number of children in a family would have what shape? So let's think about the values that might take on. A family might have no children, 1 children, probably 1 to 2 would be the most common, and then we would have some families that would have a lot of children, but very few. So we would expect this would have a skewed distribution. The distribution of wealth distribution would have one kind of a shape. When we think of wealth distribution, we think that there's a small number of people who make a lot of money, and then most of the other people don't make as much money. So this probably has a J shape. The empirical rule tells us in a normal distribution, about 68% of the data will lie within 1 standard deviation of the mean in both directions. Approximately 95% of the data will lie within 2 standard deviations of the mean in both directions. And approximately 99.7%, or basically all the data, will lie within 3 standard deviations of the mean in both directions. And here's a picture of what the empirical rule looks like. We notice in the middle of the distribution, we see the mean right here. And if we go 1 standard deviation on either side, we capture about 68% of the data. If we go 2 standard deviations, we capture about 95%. And if we go 3 standard deviations, we capture 99.7% of the data. Women's heights are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. What percent of women are between 60.8 and 66.6 inches tall? So we know that the mean is 63.7. Let's calculate the different distance from 63.7 to 60.8, and we get 2.9 inches, and that's the value of 1 standard deviation. Now let's calculate the distance from 63.7, the mean, up to 66.6, and we also get 2.9 inches, which is 1 standard deviation. And the empirical rule tells us 68% of the data will fall within 1 standard deviation of the mean. So we would expect about 68% of the women will be between 60.8 inches and 66.6 inches tall. Same example, what 95% of the women would be between what 2 heights? So the empirical rule tells us 95% of the values will fall within 2 standard deviations. So we're going to take the mean for the women, 63.7, subtract 2 standard deviations, we get 57.9 inches, and then we're going to add 2 standard deviations to the mean, and we get 69.5. So 95% of women should fall between 57.9 inches and 69.5 inches tall. What percent of women's heights are between 66.6 and 69.5? All right, so we know that 66.6 is 1 standard deviation above the mean, and 69.5 is 2 standard deviations above the mean from the prior problems. Now we know, if we look at the picture, 68% of the data will be between 2 standard deviations, and 95% will be between 3 standard deviations. So if we look at the difference between those two, 27% is going to fall between 2 and 3 standard deviations. but we're only looking on one side of the curve here. On the high side, we're going from 66.6 up to 69.5, so we would expect about 13.5% of the women to have heights in that distribution, in that region rather. Let me go back for a second. We would expect about 13.5% of the women to be between 66.6 and 69.5 inches tall. Suppose the nightly rate for a 3-star hotel in Paris is normally distributed with a mean of 160 euros and a standard deviation of 8 euros. What percent of hotels will have rates between 144 and 176? So again, how many standard deviations is 144 from 160, the mean? It's 16 euros below. The standard deviation is 8, so this is 2 standard deviations below the mean. How many standard deviations is 176 from the mean of 160? It's also 2 standard deviations. So the empirical rule tells us 95% of the hotels will have rates between 144 and 176 euros. Same scenario for the 3-star hotel. 99.7% of hotels would be expected to have rates between what 2 numbers? Okay, the empirical rule states 99.7% of the data will fall within 3 standard deviations. So on the lower side, I'm going to subtract 3 standard deviations, and I get 146, and on the upper side, I get 184. So 99.7% of the 3-star hotels in Paris are expected to have rates between $146 and $184. What percent of 3-star hotels would be expected to have a nightly rate above 160? Now notice that 160 euros is the mean. Remember, in a normal distribution, the mean is right in the middle of the distribution. 50% of the data is above it, 50% is below it. So 50% of the 3-star hotels would be expected to have a nightly rate above 160 euros. Z-scores, or standard scores, determine how far, in terms of standard deviations, a given score is from the mean of the distribution. And here's the formula that we use to find the z-score. The value of the piece of data we're interested in, subtract the mean, and then divide by the standard deviation. So let's find z-scores for 4 numbers. We have a mean of 60 and a standard deviation of 15, and we want to find the z-score for the number 75. So we're going to take the data value, 75 minus 60, we get 15, divided by the value of a standard deviation was 15, equals 1. And frequently we'll put a subscript on the z to say what number we're finding the z-score for. This is the z-score for 75. Now we want to do 81. So we're going to take 81 minus 60, we get 21. Standard deviation, 15, and we get 1.4. So 81 is 1.4 standard deviations above the mean. Now finally, 60. So we take 60 minus 60, the mean was 60, divided by 15, we get a z-score of 0. Remember, we said the mean, the data value at the mean would be right at the middle of the distribution, and it will always have a z-score of 0. And finally, 33. Now this number is below the mean, so it's going to have a negative z-score. So we take 33 minus 60, we get negative 27, divided by 15. So a value of 33 is 1.8 standard deviations below the mean.